I can do it. There,
Got it.
that's great.
Yeah, I'm not surprised because, I've made you co-host. You should be able to do what I can do. And then I'm going to do chapter 4, um, which is a cool chapter, propagation. So, yeah, Jerry, if you want to take her away.
Take her away. Okay. Let's see if we can do some things. All right. When we were last year, we did a whole bunch of radio parts and things, mostly inductors, which work on the magnetic field of the electromagnetic spectrum, and capacitors, which work on the electrical field. And we'll get them together. And I think we talked a little bit about capacitors and inductors having a kind of resistance or reactance. And when the two balance, they will pass and are connected together. They pass a signal through that's called resonance, or they can reject a signal. All right. Are there any questions for last week? Anyone has something burning in your mind? Okay. Diodes and transistors and integrated circuits. All right, these are all questions that, I guess they do a pre-test. These are all questions in the pool that you might find on your exam. Okay. A semiconductor that only allows current to flow in one direction is called a diode. I'll show you in a little bit what a diode does. Okay, let's see. Okay. This is a diode, a simple diode. The back part is called a cathode. The front part is called an anode. And I believe we saw in the book that the cathode usually has a marking stripe on it. And if you look at some of the tiny ones that I swap, you'll even see even tinier numbers that tell the characteristics. What they do, they let electrical current flow in one direction. For instance, here is something coming out of the antenna. You have sine waves here, positive parts and negative parts. After it goes through the diode, it only has the positive parts going through. Now, this is still the radio carrier, and the voice or music or whatever signal connected together. It's called heterodines together. A capacitor. Anyone know one of the things that a capacitor does aside from storing electricity? I mentioned it last week.
Discharges it fairly rapidly.
That's one function, but that's not the function we're talking about in this one. A capacitor will let alternating current pass through. In this case, it's taking the carrier here, alternating current, and passing it through to ground. In other words, it's getting rid of it. So all you have now is the audio, which is going to flap a loudspeaker up and down. So this is a demodulator. It takes the radio signal and turns it into a sound signal. So that's one purpose. Okay. Okay. Here's another purpose for a diode. Okay, you can see the transformer, which is two coils wound around a common metal core. You can see the wave here goes through the diode, and in this case, you see it only takes the positive part and doesn't allow the negative part of the AC to pass through. So what you have now is positive, nothing there, positive, nothing there, positive. So it's going to be a bumpy ride. This is called a half wave, because you see the half wave. Okay. Where is that thing? But I had that stuff. Hang on a sec. Here it is. Okay, if you have these little bump, 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 you put a capacitor in, and as Bradley was talking about, it stores electricity. When it charges up, it stores electricity, and when there's no electricity, when there's this zero part, it discharges and boosts it up, and it keeps on doing it. So instead of having a very lumpy output, it's closer and closer to direct current. There's still a little bit of lumpiness here. It's called ripple. And you can cure that by different ways. If you use a very, very large capacitor, the ripple goes way down. And there are voltage regulator circuits that will make the ripple even lower. Okay, any questions on that? Okay. Okay, there and there. Okay. Okay. Okay, this is this little arrow is just a flow of current arrow. This is the device. It's called a Zener diode, and it's a very special diode. It's rated as at different voltages. What happens is that if there's any variation, in the voltage coming out of the rectifier, this thing acts as a kind of resistor. It drops down the any higher voltages. It drops it down to something. If you have a 5-volt Zener, anything over 5 volts is going to be dropped down. So you have nothing but a steady 5 volts going through. And that's what a Zener diode does. Okay, questions? All right. Okay. Transistors. A transistor is a semiconductor device. It has 3 parts to it. You know, it's sand with various metal alloys doped into it to allow the flow of current. Current will flow between the collector and the emitter. And the base is the contact which regulates how much current is going to flow. So it's like a little hose, like use the hose example. You have the water flowing, you have the little sprayer on top of the hose, and you can modulate, you can make it greater or lower, or turn it off altogether. In this particular case, you have, see, call it an audio signal. It's going through, and the current is flowing. The audio signal varies enough to drive a loudspeaker. So if you put a microphone on this side, which is very, very low voltage, very low current, this boosts it up. And that boost is called gain. Okay, any question about that? Okay, anyone? What is this capacitor doing here?
It is storing the electrical wave till it's a higher capacity, so it's a higher voltage, and then discharging it.
It's a good answer, but it doesn't, not for this one, not for this one.
I think it's just blocking the DC from the 5 volts above so that the DC doesn't go through to the speaker.
Okay, well, what's going through the speaker then? What's going through this capacitor?
The audio that's being amplified by the transistor, the audio is going through the capacitor to the speaker, and the DC is not going through.
Okay, so what would you call the audio then? You call it AC. It would be an alternating current. That's how it gets past the capacitor. Very good. Okay. Oh, here's another thing, frequency mixing, call it. All right. We have a transmitter that is putting out an unmodulated carrier at a certain frequency. If you put an voltage that goes up and down according to a tone or a microphone or something of that sort into the power supply going to that going to the unmodulated carrier, you get a mixture of this and this going out. That's modulating, and the thing that's demodulates is what?
Demodulator.
What demodulates that? We showed you that a little earlier. It was that little diode that takes this apart and gives you the audio frequency to use. Okay. Yeah, I'm gonna stop sharing for a second. And okay. Share screen again. Okay, this is something kind of cool. I'm not sure they're going to give you a crystal oscillator or crystal, but this is a small transmitter. And this is a crystal, usually made out of the quartz mineral. And the property of a crystal is that, or sometimes you'll see it advertised as piezoelectric because of the piezoelectric effect. When you shock the crystal, it will vibrate at a certain frequency. You've probably seen the beepers and sirens and things of that sort. They're vibrating at a very low frequency that we can hear. But these can vibrate at radio frequencies as well. So what you do, you have an amplifier that makes its own feedback, just like you take a microphone and hold it next to the loudspeaker. It's going to cause feedback, vibrating sound. So you induce vibration, you induce the vibration into the output, and it keeps on feeding back. And in the output, for instance, if this is working cut to 7 megahertz, you're going to get a signal of 7 megahertz out. Put a telegraph key on this, and you have your little radio transmitter. Okay, now this is very interesting. This is a coil wrapped around some sort of iron core. And it's an inductor. What's it doing in this circuit? Well, an inductor allows direct current to pass through. But what does it do about alternating current? Anyone? It blocks alternating current. It's the direct opposite of a capacitor. Capacitor will allow alternating current to go through, but blocks direct current. This allows direct current to go through and blocks alternating current. Everyone got it?
Yep.
Hey, come on, can't hear you. All right. Okay. So, okay, they talk about mixers. A mixer is something that puts two signals together, like that modulator. And although we have different high technology, my transceiver, the IC 7300, is not a super heterodyne type of thing, which uses mixers like that. But Bob's 991, Yaesu 991A, it does. And what happens with this signal from the antenna now turns into current, and there's a crystal oscillator down here which mixes the two together, mixes the signal and the antenna signal, so it goes down to a different frequency. Now, in the old exam, they had, I guess, well, before the technology changed so much, you would sometimes have your high frequency radio working on, say, 29 megahertz, using a mixer to get it up to 144 megahertz. So you get, 144 megahertz, and let's see, what is it, 108 megahertz, I think it is, or Now, Bob, what's 144 minus 29? Bob, you there? Anybody? 144 minus 29?
115.
Okay, 115, thank you. So 115 plus, all right, 144 minus 115 equals 29, which can go into your HF transceiver. And a mixer can do the same thing in the other direction. 115 plus 29, and the output would be 144 for your transmitter. So anyway, that's what the mixer does, and that's a question that's on the exam. That's why I have to tell you about it. Okay. Here's another one. Light emitting diodes. You see it goes, the current flows, and this device changes electricity directly into light and the photons. That's all you need to know right now. When you get into general or extra class, you might need to know a little bit more about photons and things of that sort. Let's see, where is that other silly thing? Okay. Here's something. A photoresistor will actually, or call it an electric eye, will take photons and turn into, allow electricity to pass through it. In this circuit, it's on the base of the transistor. And once light flows onto the photoresistor, it allows current to flow and allows current to flow through the LED and through the transistor. So this acts as a sort of switch. Now these can be infrared, ultraviolet, or visible light. And anytime you go through an elevator door or something like that, you have one of these gizmos working on you. Okay. All right. Thyristors. A thyristor is a protective device, and it allows high voltages to pass through to protect other circuitry. Now here's an example on an AC line. Lightning strikes one of the wires in your circuit. Thyristor will divert that to ground. Hopefully protect your television set. These aren't thyristors. These are gas discharge tubes, but it's the same thing. These are antennas from my tower. They go through these protective devices. So hopefully if lightning strikes, these devices will divert it down to ground. This thing is going to a ground that's about 7 feet driven. There's a 7-foot pole that's driven into the ground that this is attached to. And hopefully that'll work. Okay. Questions on? Okay. All right. Share screen.
Gary, can you use the ground rod that is hooked to your meter, or do you have to have a separate ground rod for your antenna?
It's best to have your own separate one, although it's nice to bound all your stuff to all your equipment to the electrical ground. I have all your the antennas tuner and your transceiver and power supply, all connected. They'll talk to you later about using either a wire braid or some sort of sheet ribbon kind of metal. But it's also good to have a radio ground, which is part of this. My tower has 3 ground poles that are all connected by wires connected to the each leg of the tower, and that protects the tower from lightning. I actually use the house water pipes as a ground for the radio, for the electronic ground. Okay, let's see where you've
So
got.
I know the gas mains are starting to be replaced with plastic pipes instead of the copper and metal pipes, even up to the house. Because they came out and did mine last summer, right after I bought my house, and it's now a like plastic type pipe going into my gas meter.
That's not very good for what you're for that, and of
Yeah,
course
you should be
we
using a
got
gas
plastic.
meter line.
You got plastic water piping now too. So now you're gonna have to figure out another way, like your ground rods. Okay, let's see. All right. Okay. Okay, circuit that's generates a signal at a specific frequency. We showed you that crystal. What's it called? The answer is right here.
Oscillator.
Yes, good. Okay. An amplifier takes a weaker signal and amplifies it. And the amount of amplification is called gain. Okay, let's see. Okay. Oops. Okay, you can see this oscillator driver is a sort of intermediate stage. And the telegraph key controls what goes into the power amplifier and into your antenna. Now the magic is done in the antenna. It turns the electron flow into what?
Radio waves.
Which are, yes, and what are radio waves? They have 2 components.
Yeah, that's electromagnetic. We actually get into that in chapter 4.
Yes. Okay. See, I think that's about it. Well, when we talk about antennas and stuff, we'll talk about and feed lines. We'll talk about tuners, and they don't really tune. They just make transceivers happy. Okay. Before I turn this over to Bob, I will say that there was a book I read when I was a young cub about these guys going into darkest wildernesses in Africa, Asia, Borneo, and all that. And one of them brought radio equipment, and they were trying to explain what the radio equipment did. And the natives, and they're as intelligent as we are, of course. I know that I've seen guys whose fathers had bones in their noses become helicopter pilots, for instance. Anyway, they thought that the equipment was persuading friendly spirits to send messages for you. And actually, that's not that far off. So without further ado, Bob, take it away.
Okay. Yeah, sometimes I wish there were friendly spirits that help propagation. Yeah, okay. Hey, let's get into propagation. Let's, propagation is just how radio waves get from one antenna to your antenna, how it goes through the air. I got to tell you, I love this subject. I really do. Years ago, 40 plus years ago, when I was in the Army Reserve, that's back when the Army Reserve had one big mission, and that was to get ready to fight the Soviet Union when they advanced, across Eastern Europe. But at that time, I purchased this large radio, what used to be called a boombox, and along with an AM band and an FM band, there were two bands on that radio, and one said SW1 and the other said SW2. And being a, young curious guy, I flipped around on those channels. They were, of course, the short wave channels. And it was just fascinating stuff back at that time. Because at that time you could pick up, back at that time, all the major countries had broadcast stations on short wave, largely for international goodwill, also for propaganda, and being in the Army Reserve, I was very interested to listen to Radio Moscow to see what our enemies were saying about us. You could also pick up, Radio Havana, Cuba. Hey, another commie station. Radio Havana, Cuba, by the way, is still on the air. But anyhow,
there's still commies too.
there's still commies. Okay, but there was a lot of other excellent programming on at the time. There was Radio Deutsche Welle from Germany, and Swiss Radio International, and Radio Canada International, HCBJ out of Quito, Ecuador. All these broadcast stations from other countries beaming, their radio signals around the world. It just fascinated the heck out of me. I was just really wowed by that. And then later, as I became a ham, I still just find it just amazing. During a 10-meter contest just a while ago, I was having great luck reaching all kinds of stations in the South, like Texas, Arkansas, Louisiana, Georgia. Interestingly enough, no Ohio. But for hours and hours, I was hitting all these southern stations, even Florida. But then all of a sudden, we started getting stations from the West. And all of a sudden I was picking up Kansas and Nebraska, Colorado, Utah, Santa Clarita Valley in California. One station that I contacted in Colorado told me he was really surprised he'd been listening to the radio for the 2 days of the contest. He had never heard a Michigan station. And then all of a sudden, he said within the last hour, all of a sudden he got, 6 or 10 Michigan stations, which he had not heard, previous to that. Well, tonight we're going to touch on this phenomenon of propagation and how how your radio signal gets from one place to another. Before we do that, though, I want to do just a little. I want to go back and pick up. And of course, I can't find it right at the moment. Hang on, I'll be right there. Okay. Now, there we go. Okay, am I sharing?
Yes.
Okay. All right. When we talk about propagation, different lengths, different radio wavelengths, have different characteristics and are affected by different things. What I want to do here is just take a minute, and this is just talking a little bit back about, you know, what we picked up in chapter 2. You see, this is the radio spectrum, well, the electromagnetic spectrum, from very, very low frequency to super high frequency. It goes way beyond that on the right. It's nice if you know some of these things, but listen to this. For your test, the only things you may be tested on in this, you know, for knowing which ranges you need to know. Do you see VHF? You see that starts at 30 megahertz and it goes up to 300 megahertz. You might be asked that question, that you might be asked the question, what's the range of VHF? Or they'll give you a bunch of different options, a bunch, you know, the A through E or whatever. And that one you may be questioned on. The other two that you may be questioned on is HF, high frequency, or what's in the vernacular, that's usually called shortwave. And then, which is 3 megahertz to 30 megahertz. And the other is UHF, and that's 300 megahertz to 3 gigahertz. 3 gigahertz, you know, is 3,000 megahertz. What I want you to see here is just put in your mind VHF. And I say VHF because most of your amateur privileges, the one that you're really going to be using is probably the 2-meter band with your technician license. So, you know, you should know that that's 30 megahertz to 300 megahertz. Now, and then once you know that if that's very high frequency, just plain old high frequency would be below that. Okay, so if VHF starts at 30 megahertz, that's where HF ends. So the high limit of HF is 30 megahertz. And if you divide that 30 by 10, you get down to 3 megahertz, which is the low part of that. All right, that may appear on your test. On the high side, on the higher frequency side, the VHF band ends at 300 megahertz, and that's where the ultra high frequency, the UHF band, starts. And that goes up to, it starts at 300 megahertz, so it goes up to 3,000 megahertz. 3,000 megahertz is also 3 gigahertz. Now, if you look in that, I've kind of put, you know, little markers there where the amateur bands are. Now, this chart is actually not quite accurate with those little indicators they have for VHF TV and FM radio. You see, I've marked the 2-meter band at 144 megahertz, which you would think is probably kind of in the middle between, you know, or close to the middle between, you know, 30 and 300. FM is actually, the FM band is actually to the left of that, you know, because FM radio goes from like 87 megahertz up to 106 megahertz. So it should be to the left of that. So those are the 3 you should know. Now, there's something else I want you to notice, you know, and, you know, Jerry covered this before, but I want to, you know, kind of reiterate this. You'll notice that, let's look at the bottom of the high frequency band, you know, down just a little bit above 3 megahertz. That's getting you to the 80 meter amateur band. Okay, so it's low frequency, but a very, very long wavelength. You know, 80 meters is, well, that's getting pretty close to a football field. And as you go up in frequency, remember, as you increase in frequency, the wavelength gets shorter. So you get up to, so, you know, you're down near 3 megahertz, and that's an 80 meter wavelength. But you get up to the VHF band, you get up to 144 megahertz, and that's the 2-meter band. And 2 meters is what's that, about 6 feet 5 inches, 6 feet 6 inches. All right, so there's a big difference between 80 meters and 2 meters. Okay. What else do I need to tell you about this? Oh, that should do it. But keep those three ranges in mind. Just remember that VHF is 30 to 300 megahertz, and then you can figure out the others. Okay.
But Bob, if I could mention that, that's very helpful to see both the frequencies and the wavelengths. Is that right?
Yeah.
On
Yeah.
the same chart. Yeah.
Yeah. Yeah. It's like I confess I did that as much for me as for anyone else, and I've had that for some time now. So, okay. Now, let me go. And then before we get into the actual, I'm going to go through the actual formal presentation of chapter 4. But before we do that again, now let me give you some kind of the big picture. So we're going to talk about how radio waves get through the air. There's a couple of different ways. And then we're going to talk about antennas. Antennas matter. Now, I'm going to give you an exaggeration. It's not always true, but it's close to always true. If you have trouble contacting another station that you should be able to contact, the problem, it's not your radio, it's your antenna. Antennas matter. Now, that's not all there is to the story. Depending on the frequency that you're using, the atmosphere matters very much too, particularly the ionosphere. Okay. Now, let me get back to, let me see, do I want to give you, now I don't want to, I'll just start with this. Slideshow from the beginning. And screen share. Jerry, am I sharing?
You're sharing.
Hang on a second. Well, does it advance?
Yes.
Okay. I wanted to do this as a full slideshow, but for some reason it's not quite reacting, but that's okay. All right. Radio wave propagation, getting from point A to point B. This is cool stuff. All right, like I was saying, it depends on two things. You know what this is? Let me try this once again. Sorry, let me get back out and try this once again.
Bob, sometimes hitting F5 puts it in full screen mode.
Okay.
Thank you.
Oh. Okay, how about that?
Yep.
There you go.
Oh, okay, there we go. All right. All right. All right. When I'm saying propagation, that's a cool word. All it means is how your radio wave gets from one point to the other. there's a number of ways it can happen. One, of course, is simply line of sight. Line of sight. Now, when I'm talking about line of sight, I don't mean your line of sight. I mean the line of sight from your antenna to the target antenna. A second way, radio waves at some frequencies can travel along the ground a little bit. And of course, then there's skywave, and skywave is where you get your big distances. Line of sight. Now, remember that radio spectrum that I just showed you. Line of sight for VHF and UHF, that is essentially line of sight propagation. All right, you need kind of you don't, it's sometimes called direct path, but that's a little misleading. You don't need a completely direct path. All right. As the signal goes out from your antenna, it does spread out a little bit. It does weaken a little bit. And here they use the word attenuation, and that just means your signal is losing strength as it travels through space. And line of sight, VHF, again, that's say the 2 meter band and the 6 meter band, and UHF, those are both essentially line of sight modes. Now, ground waves, what they're talking about here is that the radio signal can follow the ground a bit, and can follow the ground further than plain line of sight. And it can go, and again, a few hundred miles, but when they're talking about a few hundred miles of ground wave, they're talking about very low frequencies. So that'd be, 80 meter band or
160.
such, or 60, yeah, but not VHF. VHF is not going to give you great ground wave propagation. Now, let's go. Okay, reflection, diffraction, refraction. Okay, radio waves are reflected over some surfaces like grounds and waters and buildings. And that can be very, very handy, by the way. That can be very, very useful. Refraction, on the other hand, means just bending a little bit through the atmosphere. And then diffraction, this is, perhaps you saw this, well, I hope you saw this in your book. Diffraction is what happens when your radio wave hits over a sharp edge, and a sharp edge meaning like the corner of a building or something. What happens is there can be an interference pattern where for some places your signal is very loud, and in some places it's a null and you're not getting much at all. And I think that's it can cause your signal to go loud and then soft and loud again. Okay. All right. For VHF, okay, there is some bending, some refraction for VHF. So you're getting a little more than distance that just is on the radio horizon. And again, we're talking about the radio horizon, not your horizon. For a person standing who's, about 5.5, 6 feet tall, standing up, looking straight out, the actual visual horizon is only about 3.5 miles. Now, if you're up on a building, all of a sudden your visual horizon is quite a bit further. Okay, and that kind of works for that principle works for your radio, because again, what we're talking about is how high is your antenna. Now, if you're using a handheld, well, the radio horizon isn't much more than the visual horizon, but well, it is actually, because your radio wave doesn't stay at ground level. it diffuses out and goes up on an angle. Okay. UHF signals can penetrate a building better than VHF because of shorter wavelengths, but VHF can reflect off buildings, which is kind of interesting. Now, a couple of things. Oh, let's see, multipath. Multipath means, your radio signal as it's going out into the world, if it's bouncing off buildings, you think back to that knife edge diffraction slide where your radio wave is being broken up. Now, your radio wave, even broken up like that into different pieces, can reach the receiver, can reach the far antenna, but it can reach as two different signals. Well, it's the same signal, but just offset by a little bit of time, by fractions of a second. But that causes kind of a fluttering in the reception. Another thing that causes that is if you're in a car and you're driving in a car and your signal is passing, think of driving through a city where your signal is bouncing off different buildings and going by different paths. That can cause a very fluttering kind of reception sound that's referred to as picket fencing. And I don't know why they think that's so important, but it often that here, let's go back a second. Multipath is something you will need to know, but also picket fencing sometimes appears on the test. So, and that's what that is. It's just that fluttering sound that comes usually from a moving transmitter, meaning you're in your car radio. You have a ham radio in your car, and you're transmitting as you're, passing buildings and other kinds of obstructions. Now, tropospheric propagation. Okay. I have a cool picture I want to show you. In fact, for tropospheric, I've got a couple of cool ones. Here's okay. Jerry, am I sharing?
You're sharing, you have the ionosphere and thermosphere.
Okay, yes.
You need layers.
Okay. All right, now here's the thing. We're way down here in what's called the troposphere. And right above us, where planes can fly is, the stratosphere. And above that, starting at about 30 miles or 50 kilometers if you're hip, all right, starting there is the ionosphere. And the ionosphere has, the ionosphere is up high enough and there's just enough particles up there so that the sun's UV rays can knock electrons free, and the electrons help your the electrons are what make radio waves bounce off the ionosphere and reflect back to Earth. The ionosphere, it's got a couple of different layers. Now, and I think we had this, and let me get to a cool one. This is a nice one that I picked out of, this is from an old Army, well, not Army, this is from an old Navy manual. And what I want you to see here, the book covered this, and I thought they did pretty well, but there's really four layers that we're concerned with. There's the what's called the D layer, which is closest to the Earth. There's that E layer. And then there's the F layer. The F layer during the day is broken down into F1 and F2. They're at a little different heights. The D layer can reflect some radio waves. It can also absorb some. So the long distance communication really comes off of the F layers, the F1 and F2 layers. There's where is, and let me, this is, let me cite this. This is a graphic from a guy named Carlos Molina. But I just thought it was such a cool graphic because it shows you where the different bands are. So during the day, you see we've got a D layer, we've got an E layer, and then an F1 and F2. But as the sun goes down, all of a sudden, that D layer pretty much goes away, and the F layer or the E layer also gets pretty weak, and then the F1 and the F2 collapse into a single layer. But it's a little lower than F2, and then it's a little denser than either of them separately. And
Yeah, Bob, yeah, can I mention something about the D layer? I think all of us have noticed if you ever listen to, well, most of you are in the Detroit area. If you listen to WWJ during the day, you're going to find not that many stations that you can listen to. That's because that D layer sort of inhibits the bouncing of radio signals. At night, when that layer goes away, the radio signals from all over. There are truckers stations down in Texas and far Midwest that you could listen to. That's because the D layer went away.
okay, all right, am I back to the presentation?
Yes.
Okay. All right, tropospheric propagation. Now this is something that's particularly useful in the VHF band when sometimes when there's a temperature inversion and where colder air gets on top of warmer air, the VHF and sometimes UHF, but mostly VHF radio waves can travel much farther than normal. Normally, for the 2-meter band, if you can get, depending on how high your antenna is, if you can get 20, 30, 40, 50 miles, you're doing pretty well. But every now and then, there's this inversion and your radio wave, it's like it's almost in a duct and it just gets carried, much further. Those of you who live in the Detroit area, there's a classical music station called WRCJ, and one of the presenters on that, the early morning guy, Dave Wagner, also happens to be a ham radio operator, and on the radio, he calls himself Dr. Dave because he has a PhD in music. But his call sign is W8DRD, Dr. Dave. At any rate, back when I was still working, and this would have been around 2015 or so, I was on my way to work on a Monday morning, and I was listening to him. It was about I don't know, 6:45 in the morning, and he was talking about how the night before he had been on the radio, and he had been on the 2-meter band, and all of a sudden he started hearing operators from Chicago about, and that's not quite 300 miles away, but that's a long ways away. That does happen, and it's wonderful when it does. Okay, now, yeah,
Bob, can I share?
yes, go ahead.
Okay, yeah.
Do you want me to stop sharing?
Yeah, for a second.
Go ahead.
Okay, let's see if I can get this going. Here it is. Okay, internet is beautiful in that it can give you all sorts of good information. You can find maps that show tropospheric ducting. And if you are within any of these regions, and as you can see, the coloring is how intense the ducting is. You can talk to someone from here to there. And I've heard of guys sitting in their house in Huntington Woods talking to someone in the Upper Peninsula, if the conditions are right. So, well, that's one of the really nice things, and it's mostly 2 meters. 6 meters got some of that too.
Can you guys hear me?
Yes, I can.
Quick question about this ionosphere and the split between day and night, and
Yes.
how the F band, splits into two. Is that just due to the solar radiation during the daylight being stronger, and that's what's causing that? Or what's the actual, I understand the effect, but what's the cause of those bands to be more of them during the day versus at night?
Yeah, and you're right. It is the fact that that part of the Earth is no longer in direct sunlight, and the sunlight is what affects those layers of the ionosphere.
Gotcha. Awesome. Thank you.
Yeah.
You're gonna
Bob and Gary, I'm sorry to interrupt, but I actually had a follow-up question to Clayton's because I thought that was very interesting. Is it safe to say that one can get less of a signal in the day versus night in terms of propagation of a radio communication, or the opposite? Because when those bands collapse or the ionosphere collapses, can I expect a stronger or a weaker propagation of my radio signal?
Kurt, it depends what frequency you're working on. Now, if you're in the 10-meter band, say around 28 megahertz, that's a band that, interestingly enough, during its best from about dawn till just after sunset. Okay. Now, and I think the reason for that is that it reflects off the lower parts of the atmosphere, which are more active at that time, I think. But that's the 10-meter band. Now, as you go lower in frequency, they get more active at night. When you get to the 40-meter band, you normally get, a lot better distance at night. The 40-meter band is where a lot of people do very, very long distance communication.
And is that I'm sorry, last follow-up, I promise. Is that related to the electromagnetic signal either penetrating whether it's the ionosphere or something, or reflecting, and the different densities or whatever of the ionosphere, when you send a signal, it depends on what frequency, whether it will pass right through or bounce off. Is that correct?
Exactly. Yeah, exactly. And the thing is, you get to nighttime and, you think that you're getting there's less interference in the lower levels, so less is being absorbed, and it goes up to the F level, which is then combined, And since it's higher, think of like a pool table shot, where you get a longer angle and you can get further distance.
Got it. Thank you very much.
Sure.
Okay.
Hey, and for all of you, as we go along in this, hey, if you have a question, pop up, Oh yeah, please don't wait till the end. Just when you got a question, you ask about it.
So I had something on the ground plane or ground wave antennas.
Okay.
When I was in the Army, we were switching our antennas over, and the antennas we got were capable of that. Simultaneously of being able to be hoisted in the air on a rope over a tree branch or hoisted up by a pole, like a gin pole.
Mm-hmm.
So from my experience, you're going to get maybe 5-10 miles off a ground plane antenna.
Yeah.
Unless you're
Brad,
like
do you
perfectly
remember what
flat,
frequency? Oh, sorry, go ahead.
like perfectly flat plane,
Yeah.
you can maybe get a couple 100 miles, but any hills or anything will ruin your chances.
Brad, do you remember what frequencies you were operating on?
I do not, and all the frequencies that I would remember were all encrypted.
Oh yeah, well yeah, but I just kind of wondered, whether it was VHF or I would expect it would be. I would expect it would have been VHF.
It was
but I
the
don't know
FM
that.
frequencies because we did do FM. I do remember that.
Yeah, but yeah.
We
Okay,
didn't get too much. I didn't get too deep into the radio theory part of it because I was just trained as a base operator. Because I had a security clearance, I could handle the equipment to encrypt the radios. So lucky me, I got assigned extra duties because I had a security clearance.
Yeah.
Bob, I'm wondering whether Brad is talking about NVIS, which
Near vertical incident skywave.
right, which bounces off the almost straight up, so you can get a good consistent couple 100 miles. Because as far as real ground wave, as far as my my history lectures and stuff, back in the teens and 20s, commercial stations would operate on very, very low frequencies. There's one left. It's in Sweden, and it would it would go thousands of miles via ground wave. But you're talking about a frequency of about 17 kilohertz, which is way down there.
Yeah.
But as far as we don't depend on ground wave quite as much. I think it's the excitation of the ions in the ionosphere that affects the reflection of the radio waves, and that depends on, well, you're going to get into sunspots and all that sort of stuff, and our suffering and now our ecstasy.
Yeah, and you think about low frequency transmitting. You remember it was I think it's been a couple of decades, but you remember there used to be an ELF, an extremely low frequency antenna up in the Upper Peninsula. It was a military thing, and it was extremely low frequency, so it was extremely long waves, wavelength. Now, their antenna, which was buried in the ground, was like 2 miles long. There's a relationship between the wavelength. As the wavelength gets longer, the antenna you need to really receive it or send it gets longer. So that extremely low frequency system was meant to communicate with submarines, submerged submarines, but that's been decommissioned and it's not there anymore.
Bob, I just saw that special on I don't know if it was National Geographic or whatever. I was going to ask that question, like what wavelength would that be that you can go a couple miles underwater? So thank you for mentioning that. That was really cool.
Yeah,
Those
yeah.
old-
And you know, it's like that, you remember that, well, that, where's okay, yeah, you remember this thing that I showed, this chart with very low frequency at 3,000 or 3 kilohertz. This was not very low frequencies, it was extremely low frequencies. So it was, um, yeah, that would have been frequencies below 3 kilohertz. So
What would be an example of a wavelength in that band? I mean, is that like 500 meters or something?
Oh, no, it's much lower than that.
Wow.
Much, no, thousands of meters.
Oh,
Thereabouts. No, the stations that I mentioned operating at 17 kilohertz. Actually, they used alternators to generate the radio waves rather than tubes, and they were put into service during World War II because their waves could penetrate somewhere around 100, 150 feet below seawater.
wow. Amazing. Thank you.
okay,
So-
while we're talking about night and day, let me there's something called where it's that part of the earth where you switch from night to day. There's a region that's referred to as the gray line, and that's just at that point where you go 100 miles in one direction and it's night, you go 100 miles in the other direction, it's day. And it's the same thing here. We have a difference in the night region and the day region. And as I said, you get to the nighttime and there could be some E layer, or sometimes the E layer completely disappears and all you got is the F layer there. So, and of course, the F layer being higher up, you get that cue ball effect, where you get a larger banking shot. So, anyhow,
And Bob, to
I
answer,
tell you, the propagation is such a cool subject, isn't it? I mean, I just love it. So,
and to answer your question earlier, Bob, looking at the chart again for
Yeah.
for FM FEL, it was VHF, so we did run in VHF because we were on the FM frequencies.
yeah, okay.
I just don't remember which exact specific frequencies they were.
Yeah, I kind of, Brad, I kind of thought it was in that range, but I just, when I was in the Army, it was a lot further back in history than when you were. So,
Yeah, we were using the SINGARS radios when I was in. I'm not sure which ones you guys, I think you had the ones before the predecessors, because I think the SINGARS came out in the 70s
oh yeah,
or early 80s.
okay. It was kind of funny. My first MOS was 13 Echo, Field Artillery Fire Direction. They trained us, they had a computer for it. And this was, and again, in the 1970s, the computer was, I mean, it was huge. I mean, it was much larger than a normal television. It weighed about 90 pounds. And but by the end of the 1970s, Texas Instrument actually had a programmable calculator that could actually do the firing data, and could do it faster. So yeah,
That's amazing.
I know. So okay, hey, the ionosphere. It's just so cool. Okay, 30 miles or 50 kilometers, 30 miles to 260 miles above the Earth. Yeah, and it's thin enough for the atoms to be ionized. Ions, yeah, they're electrically, it's the ions that are electrically conductive. When I say the ultraviolet radiation from the sun, knocks loose some electrons. Well, when you take an atom and knock loose an electron, well, you've got a free electron flowing around, but you also then have an ionized, well, the remaining atom is an ion because it's now electrically charged. It's no longer electrically neutral. That free electron can go combine with some other atom and make that, again, no longer electrically neutral, but electrically negative. Anyhow, that's
Bob, I have to share this. My son's joke when he was taking high school physics. One atom says to the other, "Dang, I lost an electron. Are you positive?" Yes.
Okay. All right. All right. And yes, ionization varies with solar illumination hour to hour. And that's why, in depending on the hour of the day, some bands work and some don't. Okay. Oh, and that's the big thing. Higher ionization refracts or bends radio waves more strongly. So the more ionized the atmosphere is, the easier it is for radio waves to bounce off the ionosphere. Okay, and
Wait, so Bob, sorry, quick question. Is the atmosphere more ionized? When is the atmosphere more ionized and when is it not, generally speaking?
Generally speaking, when there are more sunspots.
Okay. All right.
Okay. And that's what we're getting to right now is the sunspot cycle. Yeah, because Kurt, the thing is, when sunspots are at a minimum, it can be very poorly ionized day and night. But
which means if you wanted to contact distant stations, try for Alpha Centauri because the radio waves are going straight through the ionosphere.
Yeah.
Okay.
Okay. All right. The sunspot cycle. This is what's important because it's that energy kicked off by the sun that ionizes our atmosphere. Okay. Radiation and the sunspot cycle. There's a regular cycle of sunspots. It's an 11-year cycle, and it repeats and it repeats and repeats. And let me show you how it repeats. This is another thing that's just kind of cool. Some people there have been brilliant people throughout the ages, and some of these brilliant people have been monitoring sunspots for several hundred years. So, we know what the sunspots have been doing, for a long, long time. Right now, when back in the 1600s, there was this thing they called the Maunder minimum, where there was, horribly low levels of sunspot activity. Of course, it didn't matter back then. There were no radios. But you get up to the 1900s and you see there's been, varying amounts of sunspot activity, and it varies. You see each of these peaks, they're different by about 11 years, and there's minimums and maximums within each cycle, but each cycle lasts about 11 years. If you come down here to the bottom of the picture, you see that what they've labeled here is cycle 24, which started around 2009, ended up around 2021. You notice that it had much lower activity than previous cycles. During this time, it was the 10-meter band. You people as technicians, you will have some privileges, for some voice privileges in the 10-meter band. back then, during cycle 24, especially toward the end of cycle 24, 2018, 2019, 2020, sunspot activity was just terrible. And the 10-meter band was closed most of the time. We're now in cycle 25, and it's an upswing, and it looks like it's going to be a stronger cycle than cycle 24. Okay, that's not going to be on your test, but I just think that's just so cool that you should know about it. Okay. Let me go. All right, I'll go back to work. I'll go back to the presentation. All right. Yeah, the ionosphere, and they sometimes refer to it as RF, a radio frequency mirror, in that it reflects radio waves back to the Earth. Now, here's the deal, and this is an important thing to know, and that is, this is what we're starting to talk about here are maximum usable frequencies and minimum usable frequencies. You see, if you get lower than the minimum usable frequency, what happens is, your radio wave comes off here, but it gets absorbed in the ionosphere and goes nowhere. Now, if you're above the maximum usable frequency, and again, what we're talking about is maximum usable frequency for distance communication. If you're above that, your radio wave shoots right through the atmosphere. It does not bounce off the ionosphere. This is not always bad, by the way, because this is what you have to do if you want to, you need a high frequency, and normally, but not always, normally the 2-meter band, 144 megahertz, will shoot right through the atmosphere. Now, the interesting thing about that, and the useful thing about that, is if you want to communicate with a space station, if you want to communicate with the International Space Station, or if you want to try and bounce your signal off the moon, you need something that's going to go right through the atmosphere and not be bent. Okay, so the fact that some radio waves shoot through the atmosphere is not all bad. But if you're in California and you want to talk to Germany or Russia or something like that, you certainly need your radio wave to refract off or to reflect off the ionosphere.
Okay, Bob, can I shoot something through?
Sure. Do you want me to stop sharing?
Yeah, please.
You got it.
Okay, where'd it go? Here it is. Okay. There are a number of radio stations all over the world which shoot radio signals straight up and see what bounces and reflects. And I've got this reading. It tells you what the every 7 minutes it does this measurement, and for this time of day, it shows the maximum usable frequency of 26.4 megahertz. And somewhere here, I think it has the lowest frequency, which is bouncing. I'm trying to think whether it's possibly 3.44 or thereabouts for the lowest usable frequency. Now, here's a listing of the ionograms. Oh, estimate interval 100. No, it's not that. Anyway, these are, you can check from time to time to see what it is. For right about now, the maximum usable frequency is going down, which means that the higher bands are not going to be useful anymore. 17.9 megahertz is at this point. There is a ham band at 17.068. No, 18.068. So you might still have a shot. So anyway, that's what it is.
Okay.
Okay, all yours, Bob.
Share. Okay. Oh, and there's this thing called skip. Um, and this is responsible for over the horizon on HF and the lower VHF bands. Here they're saying 10 meters as VHF. Really, we consider that the high end of HF, but the 6 meter band is definitely VHF. But this skip doesn't normally happen on the 2 meter band, which is 144 megahertz. Signals can take many paths, sure. There is something that's referred to as a long path. Speaking of many paths, and if you're in the Detroit area here and you want to reach New York, of course, you're going to face east. You're going to put your directional antenna facing east. But, there are those times when if propagation is particularly good, you can, do the Columbus route and go around the world the other way and hit the same target. That takes some power and it takes some skill, but it can be done. Yeah. Oh, and here we're getting to this concept of randomly combining signals at the receiving antenna can either, and this is the same thing we were talking about with knife edge diffraction, is that, when a signal kind of gets arriving at a destination by two different paths, sometimes that can make the radio signal very, very loud if they arrive in phase, or we haven't talked about phase too much yet, so forget that, but it can be very, very loud, or the signals can come in such a way that they cancel each other out, and you get very faded signals or no signals whatsoever. Okay. All right, sporadic E. This is another thing. Sporadic E. It's when there are highly ionized patches in the E layer. Now, that E layer, again, it's not that high up, but it can become highly ionized in a number of different ways, and you can bounce your signal off that. Two ways are from an aurora, the aurora borealis or the northern lights, and the other is through meteor scatter. You can actually, as a meteor passes through the atmosphere, it leaves an ionized trail that lasts for, from a few seconds to a few minutes. And you can actually bounce a signal off that, but that signal can be quite distorted. One thing I do in one thing which is a normal part of my teaching method is I steal lots of files from other, and I shouldn't say I steal, because I have a couple of files here that I've gotten from Jerry. Plagiarism.
I plead the fifth.
Okay. Hey, but listen to this. When we say that signals coming off, bounced off these highly ionized things in the E layer, that they're distorted. Let me share with you what that sounds like. Can you hear this?
A little louder.
Yeah.
Okay, that's what a radio signal bouncing off a meteor trail sounds like. Now, let me see. Let me see if I can share this. Okay. All right. Damn it. Now my controls are in the way here.
Bob, do they still have that question about Aurora, about signals coming from almost any direction?
Okay. Oh, let me. Okay. All right. That was what something coming off the Aurora sounds like. Now, if you were listening to that, you heard one voice very clearly. That was a Victor Echo station. So that's a Canadian station. That was the station that was transmitting. The other station, the Kilo Echo something station, that was the one that was coming, that was having to bounce off the Aurora. And you heard how distorted that sound, you know? But that's still kind of cool, isn't it? You notice that was on 50 megahertz. 50 megahertz is in the 6 meter band. When you get your technician license, you do have privileges in the 6 meter band. So you will be able to do that if you wish. It takes some doing. I have not accomplished that myself, but some people do. All right. Jerry, what was that question? You had a question.
Right.
Or a comment.
I was wondering whether they still had that question about the direction in which an Aurora signal comes from. Because I think
I don't remember that as one of the questions.
it seemed that everything came from everywhere. There's
Yeah.
no direction to it.
Yeah.
That's probably the Aurora.
Yeah.
Okay, well, anyway, I don't see it there either, so maybe we don't have it.
Okay. All right. The highly ionized part. Okay, best on 2 meters, or 2 meters, 6 meters, and 10 meters. The auroras near the north or the south poles they can reflect, but with a distinctive distorted sound, and you heard it. A meteor scatter, you heard what that sounded like. And again, meteor trails only last a very, very short time. So, you kind of got to be on the ball. You have to be kind of like a ham radio super jock, to do that. Okay. Oh, and they say contacts can go up to 1,500 miles, but because again, you're bouncing your signal off something quite high in the atmosphere. Okay, that's the first part. Now, hang on. And you know what, Jerry, what's really funny is that I kind of always worry about having enough to talk about. But it looks like I'm going to go over PowerPoint files. Yes.
Oops. Well, you're sharing quite a bit of really good information.
Oh, okay. Oh, is all this sharing? How cool is that?
Mhm.
All right.
Okay, go back to your sharing now.
Am I sharing?
Not yet.
Oh, I thought. Hang on. Getting there. Getting there. All right. Yeah. Okay.
Okay, you're there.
And so F5 doesn't seem to do anything either. Let me
Bottom right, see the bottom of the right of the screen, looks like a little square with an arrow at the bottom. All keep going right. Nope, a little bit left. It's adjacent to the left right toggle. Yes, click that.
okay.
Puts it in slide mode.
This one right here.
It's the bottom right of the screen. You see the minus plus. It's just left to the minus. There you go, right there. Yep, that thing. Get the tip of your cursor on it.
Ah,
There you go.
thank you.
Anytime.
Okay, antennas. All right, antennas. Like I say, it's an exaggeration to say if you're having a problem, it's always your antenna, but antennas are so critically important. In your antenna system, there's a couple of things we need to consider. First off, there is your antenna, but your antenna sits away from your radio. And so the way you connect your antenna to your radio, the feed line, is also tremendously important. Now, we're going to talk about some things. Elements, conducting parts of the antenna, designed to radiate or receive. You know, this will be easier to do this. Okay. You know what? It might help you to maximize me for a second. Because I'm going to talk about elements. Now this, if I stand
That's
back.
a cool antenna.
This,
Yeah, 10 on this.
this is a marvelous piece of engineering. This is brilliant. This is a 2-meter antenna, and it was built by Hugh, K-E-8-B-E-D. I was having trouble a couple of years ago hitting the repeater because I was using a vertical antenna. And so he built me this. This is, it's a directional antenna. It's called a Yagi, okay? But anyhow, we're starting to talk about elements. Now, these are the elements, all right? And what they do is they direct the radio wave here and direct it to the important, this is called the driven element. And it's the driven element because, see, this is where the coax connects. The coax goes into here, and this is what connects to the radio. All right, the coax cable goes all the way to the radio. These others are not connected. That they are sometimes called parasitic elements, but in a Yagi antenna, here, let me. I hope you can see that well enough. But anyhow. we're not going to get into this in any kind of detail, but you just know that there's a mathematical formula that says how long each of these must be, the length of them, the front or the directing part, because this antenna shoots the radio wave that way. So these elements are a little shorter. They're increasing in length, and up till you get to the driven element, the one that connects to the radio. And then behind there, this is called a reflector. Okay. Now, you know what? While I've got it right in my hand, I'm going to go with one other. We'll get to another slide about this, but there's a concept called polarity. Do you know? Jerry had told you earlier that the radio wave is made up of two parts, an electrical wave and a magnetic wave, okay? And the electrical wave and the magnetic waves are at right angles to each other. Now, the electrical wave is what determines what we call the polarity of the antenna. And the polarity just means by itself, it doesn't mean anything unless you're trying to send your radio signal out to another antenna. Because if you have, all right, your polarity is determined by by the electrical part of the wave, not the magnetic part. So this would be a horizontal wave, horizontally polarized wave. If the other antenna is polarized the same way, you'll get the maximum reception. But if the other antenna is polarized vertically, where their electrical wave is perpendicular to the earth, and it's magnetic wave is horizontal, it's going to degrade your reception. All right, because it's not going to be. You'll still receive, but it'll just be less efficient, and you'll get less signal strength. Right now, this is set up for vertical polarization, and this is what I use to hit the repeater, one of our FM receivers. During the weekend, we're going to be doing a different kind of contest where we're going to need a vertical or a horizontal polarization. So I'll take this little joint off here, and when I put it up on my mast, it will be like this, and that will be horizontal polarization. We haven't gone through those concepts yet, but I just wanted to show you that. So when we get there, you got some background. Okay, let me go back. How am I doing on time? I'm
About 12 minutes.
Oh boy, I either better talk fast or where's my screen?
I'm sure they wouldn't mind going a few minutes over.
No, I'll have to just pick up next week because it's going to be more than just a few
It's
minutes.
super interesting, so I appreciate the additional context. Thanks.
Okay, thank you.
Yeah, I agree, definitely. Worth the
Okay,
time.
so we talked about the elements. We talked about the driven element, the one that is connected to the transmitter, and then there's something called an array, and that's when you have more than one antenna all doing the same thing. And I told you the parasitic elements, those are the ones that are not connected to the coaxial cable or whatever.
Well, Bob, it's something like a magnifying glass. It takes your radio wave and focuses it in beams, sort of. I have a rotating antenna on a tower, and you can see how finely tuned, how fine that beam is when you go around the world's rotate thing to different countries. You can zero in on the maximum strength that way.
Okay. Okay, and we've been over, resonant. Keep that concept in the back of your head. We'll talk about that more later. But resonant is just when you've, we haven't talked about,
We talked a little bit about the tuned
a
circuit.
little bit, yeah, we talked a little bit about it, but it's resonant when your feed point, when the impedance on your antenna is matches the impedance on your feed line. Okay, that will just take that as a point of faith, because we're going to talk about some more issues that'll make that make more sense. Okay, radio waves are electromagnetic, and they are indeed. Where's my share?
It's there.
And that's what it looks like. See? Yeah.
It got really small, Bob.
I can make it larger, but you know what? See that cool animation? Once I make that larger, I think that stops. Oh no, it's still going. All right. All right, Mike, is it big? It's bigger now, right?
Yep. It's great now.
Okay. Okay. That's funny, and I've done that in the past, and the animation went away. Okay, this is the important concept: is that the magnetic field and the electrical field, they are at right angles to each other. And when you're thinking about polarization, what you're thinking about is, how is the electrical field oriented? Is it parallel to the Earth, or is it perpendicular to the Earth? Okay. And all right, back to work. All right. Yes, the waves and current, they have the same frequency. And created by alternating current. Yes, yes. Oh, and polarization. Okay, here's the thing. Now, we talked about vertical and horizontal polarization, and that's particularly important for VHF. Now, remember that spectrum chart that I showed you at the beginning. VHF, the 2-meter band, for instance, also the 6-meter band, polarization matters. And because, again, it's basically line of sight. So my signal is going right to your antenna and directly. Now, when you get down to the lower frequencies, though, into the HF frequencies, the longer wavelengths, what you're doing is you're bouncing your signal off the ionosphere. And an interesting thing happens is that your vertically polarized signal, or your horizontally polarized signal, bounces off the ionosphere, gets twisted around, and at the receiving station, it's getting a circularly polarized signal, or I'm sorry, yes, they call it elliptically polarized. So for an elliptically polarized signal, it doesn't matter if your receiving antenna is vertically polarized or horizontally polarized. It's fine. But again, at VHF frequencies, vertical and horizontal polarization matter. Okay, cross polarization. Oh, yeah, and that's what we've talked about. Yes, cross polarization. That's when the transmitting antenna is vertically polarized and the receiving antenna is horizontally polarized. Yes, it's not good for VHF, but for HF, for the shortwave bands, the received signal will be elliptically polarized anyway, so it doesn't really matter. Decibels. All right. Now, I want you all to remember these three numbers: 3, 10, and -6. Whenever you hear the word decibel, until after you pass your technician exam, I want you to remember three numbers: 3, 10, and -6. See, the thing is, decibels, they're measured in logarithms. Now, many of us have been out of high school for a long, long time. And if you're not in an engineering type career, you probably haven't dealt with logarithms since you were 17. And so, and we're not in a position here to teach you logarithms. There are only three possible questions that can appear on your exam that deal with logarithms. And the answers to them are either 3, 10, or -6. When we go over the questions, I'll show you those exactly. And keep those numbers in memory until after you pass the exam.
Got it.
Okay.
Thanks.
Yeah, it's just a, Jerry, when he started out, and I love this, he described the technician exam and the material in the technician class as the material is, the area the material covers is a mile wide, but it's only 1 inch deep, so really that's all you're going to need to know about decibels. For those of you who are really into that and want to get into it, oh, great, more power to you. But for the rest of us, I think it's just easier to memorize those three answers and move on. Your book talks about it a little more, and your book actually shows you the three questions. And so like the one is, if you're increasing power from, I think it was from 20 to up to 200. Okay, well, the answer there is 10. When the power is increasing from 5 up to 10, the answer is 3. When the power drops from, I think the question said from 12 down to 6, I think, or down to 2. There's only one question that asks you about a power drop, and the answer to that is -6. Okay. All right. Now some stuff about antennas, and this. Oh, how are we doing? You know what? We're at 9 o'clock, and and there's a lot to go. So I just say, you know what? Let's just wait until next week. This is cool. We'll pick back up. There's I've got about another half hour to go, and so that's more than we can really handle for the moment.
Sounds good. Thank you, gentlemen.
Okay. All righty.
Okay,
Yes,
save your
thank
questions
you.
for next week, or else
Yeah.
email us. I think all of us have our call letters at arrl.net, or in the
Not me.
introductory stuff that Bob sent you. So
Okay.
just don't call us at 2 a.m, okay? We can't handle that.
Okay. Great. Thank you very much. And like I say, I just love this. There's all different kinds of material in ham radio, but this is just one of those subjects I really like. It really turns me on. Okay.
It's very,
so I'll
very
finish this
interesting.
up. Oh, thank you.
Very interesting.
Yeah.
Thank you very much.
Okay. Hey, good night, everyone. I'll see
See
you
you
next
next
week.
week.
Thank
Okay.
you.
Good night.
Good-
See everyone next week.
Right.
Good evening,
Well,
everyone.
Take care.
Hey, Jerry,
Yeah.
I emailed that to you, so check your email. And
Yes, it's GMRS only.
no, it's not. It's 2 meter 440. I bought one.
Well, it doesn't. It says okay. what do you have to do? Unsolder something or what?
No, it does GMRS also.
Okay, fine. As a
I
ham,
got the
we're
kit right here in the box.
yeah. That sounds great. So I'll take a look at it myself.
Yeah.
Hey, Jerry.
Yeah,
Jerry, did you notice I'm using the old slides?
yeah.
I went through the new
Does it
slides.
matter?
I don't like them as much, because they don't, or at least for chapter 4, they don't have a lot of the illustrations in with the slides. So yeah, and the slides are very, very wordy. There's a lot of
Well, that's what I'm noticing too with my slides, is they're just wordy as all get out.
They hired somebody else to-
Mike, what I'll do is I'll send you the old slides. I don't know if the old slides are still available, but I have them, so I can send you the old slides for.
Yeah, that'd be great.
Yeah,
I was gonna ask you if you minded if I did some altering.
alter all you want,
Sweet.
and add stuff and take stuff out if you don't like, So, but
Yeah,
I'll send you the old slides
cover
for chapter
questions
7 and
are
8.
Perfect, thank you.
Okay.
Great. All right, so we'll talk to you later in the week if we're going to talk about how to raise money for the club.
Yeah, you know what? I want to go to that Vintage Electronic Expo and see how big theirs is. The last time I went to theirs, they used to just call it Michigan Antique Radio Club,
Yeah.
MARC, M-A-R-C. But the last time I went, they were out in, was it Farmington Hills, or they were near 11 Mile and Farmington.
Are they still
Near Mercy College. Near Mercy College out there. Anyhow,
Are they still Saturdays? Are they on Saturday or?
yes, they're on Saturday.
Unfortunate.
Oh, yeah, right. That's right. That's the
Okay,
Sabbath.
well, yeah, give us good report.
Okay. But the last time I was there, they had well over 1,000 people through. So, that's like 3 or 4 times what our swap was drawing. So, okay,
Hey,
gentlemen,
Bob.
see ya.
Hey, Bob.
Yes.
Hey, somebody had an idea a couple of months ago. I don't remember who it was. Somebody from the club, and it might have been, I can't remember what his name is. Who's the guy who ran the ISS thing? He's teaching.
Joe
Teaching,
was on that.
teaching the extra class.
Yeah, Joe Resnick.
Joe. It might have been Joe, but I'm not sure. But here was the idea. I just want to make sure that it's not my idea.
Okay.
But I love the idea. And that the idea is at our swap, put a table up and offer. We'll program your handheld, your Waxom or your whatever, for free. And so in thinking about that, because I'm doing that for the CERT guys, I'm programming all the radios for them. I have this little laptop that's a million years old that I have all set up for with Chirp. And I programmed, Noreen was having trouble with her radio. And so I just reprogrammed her. It took us all of 5 minutes. Gave her all the repeaters in Wayne, Oakland, and Macomb County, and she was done. So where I'm going with this is we could set up a table, offer a couple of different things. Here you can have option A is just Oakland County, option B is this, option C is that. Whatever they want, I can have a couple options set up. And I can just sit there and I can program people's radios for them all day long. So if you want to add that, I'm willing to raise my hand and say, that's a service we could provide to maybe pull more people out.
Sounds nice.
That is.
Mike, are you using Chirp for that?
Yes.
Okay, I'll have to talk to you about that. I am having so many problems getting Chirp to work on this computer.
Well, and you know why? Yeah,
Probably not.
with Windows 11, they have a lot of automatic updates. And the problem that a lot of people are having is it is deciding to update your driver for you. And then when you go back and say, no, 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 and you delete their driver and you put your old driver or the old driver in that you want for your programming cable, as soon as you reboot, it says, hey, wait a minute, that ain't right. Let's put that new.
That's the Windows 11. I've got Windows 10 and still having problems with the doggone thing.
Yeah, so
Doesn't
now I'm
even-
not familiar with it doing it. Oh, no, you know what? It was doing it with Windows 10 also. Because I have a Windows 10. This the little laptop, the ancient laptop that I'm using is a Windows 7. And I've shut off all updates and everything. The only time I ever go to the internet with it is to grab a new chirp. Other than that, I completely remove it, so I'm not doing any updates at all. And so it's prime for that. If you want me to bring it to a meeting, and you can bring your handheld to the meeting, bring your programming cable, and we'll do it up.
Okay, well, I'd rather be able to do it myself since I've got a few different radios and.
Yeah, and I
do
totally
have a
get
Windows.
that.
I have a
I
desktop.
totally get that, but there's the problem you got. So now that you know what the problem is,
Okay, so I'll put it back on the Windows 7 computer.
yeah, here you go.
Great, thank you very much, Mike.
No problem.
Okay, see you guys.
All right, fellas,
Good night.
be well.
Good night.